Hi, all. Now we are on Chapter 9, Section 3. So that is our chemical equilibrium. And we've talked a little bit about equilibrium before. So some chemical reactions are going to form a product, but can also reverse and reform the reactants. Those are reversible reactions, and we represent those with these double-sided arrows. So a way to think about this is, for example, if you have a basketball team, some players are on the court and some players are on the bench. And at different parts of the game, some players are going to sit down and some are going to get up. So you're going to have different numbers of players that are on the court compared to on the bench. But whenever they swap out, right, that's got to be maintained, that number. It's got to be the same number of players on the court the entire time. So the same number of players that get up off the bench need to be the same number of players that go and sit down, right? So you can kind of think of it that way, just metaphorically. So the generation of ammonia, that's one reversible reaction. So once ammonia is formed, it can reverse and form nitrogen and hydrogen again, right? So it can move this way and can move that way, hence the double-sided arrows. So eventually, the rate of the formation of the ammonia and the rate of the reformation of that nitrogen, all right, and hydrogen gases are going to become equal. So this state that is equal is a balance of those rates of reaction, and that's called chemical equilibrium. Here's one of your definitions, right? So write this down. And once again, you can see we use our forward and reverse arrows if that's taking place simultaneously, and that's a reversible reaction. So there is no net change in amounts. That's kind of what I was explaining with that metaphor. There's no net change in those amounts because the rates of the reaction is equal, right? Equilibrium. Okay. So as long as this reaction is contained somewhat, you can definitely reform those products. All right. Now, whenever we're talking about equilibrium, there's going to be a constant there that we can refer to. So we think about that reaction we were just looking at. If you're going to measure how much ammonia is there, nitrogen and hydrogen, and in the formation of ammonia, the ratio of products to reactions is going to be constant, right? Because there's an equilibrium there. And that's called the equilibrium constant. We're going to represent that with K. So this will change at different temperatures, but for now, we're just going to look at and assume one given temperature. So K is our equilibrium constant. And we're going to have equilibrium constants for different materials. You're going to see we're going to have an equilibrium constant for a K for acids, a K for bases, and a K for water. We'll get there. So you can see that the equation, this ratio that I'm talking about, so K equals the products over reactants. So K equals concentration of your products over your concentration of your reactants, right? So for some reason, I guess those brackets didn't show up, but that means the molar concentration of. So the equilibrium constant is equal to the molar concentration of the products over the molar concentration of the reactants. And so if K is 1, you're going to understand the ratio of products to reactants. If they're equal, K is going to be equal to 1. So if something is greater or less than K, it's going to give you a reference to how much products and reactants are there relative to each other. And what do I mean by that? Oh, this is crazy right here. I'm not sure why this is happening this way. It's this format for some reason. It doesn't work out. But this is supposed to say this, and you can look at your PowerPoint, of course. Okay, so what I was saying earlier, we were talking about K, the equilibrium constant, that if there are more than one reactant or product, the concentrations are going to be multiplied together. So you can look at the equations on this PowerPoint. The superscripts, right, in the expression come from the coefficients or number of moles that are going to be in a balanced equation. So for an equilibrium reaction, that's going to look like this. If you're trying to find the equilibrium, you would use a similar formula that you will find on your blue PowerPoint slide. But whenever you have a solid or a liquid, whenever that state of matter is indicated, we're not going to have the equilibrium expression because the concentrations aren't really changing with solids and liquids. All right, it's not the same. So we're going to discount adding those in the equation whenever we come across them. So here's kind of what I was talking about whenever I was saying in reference to K, you can tell how many products and reactants there are. So if you have K and you have your products over your reactants, all right, so that is a ratio of your products to your reactants. So if they are the same, if the products to reactants is the same, then K, your equilibrium constant, is going to equal to 1. You have equal number of products and reactants. So that's like saying 1 to 1 or 1 over 1. All right, so that's 1. Then K equals 1, and that rarely happens that it's exactly so this way. Then if you have a K that is greater than 1, that indicates that there are more products than reactants. Because if you have K is equal to concentration of products over concentration of reactants for equilibrium, then if you have, let's say, 2 for your products over 1, your K is going to be, your ratio is 2 to 1. So 2 is greater than 1, right? So if you look at what that number is in reference to 1, it tells you how the products relate to the reactants, if they're larger or smaller, right? Because based on what's in the numerator or denominator, you'll get an answer that's greater than or less than 1. So if you have a value of K that is less than 1, it's less than 1, then that means you must have less in the products than you do in the reactants. And so if you write that out that way, or you write 1 to 2, 1 over 2, what's that? 0.5, that's less than 1. That's less than 1. So that value for that K gives you an indicator of how much you have there in terms of the products and the reactants, and you can tell which one predominates. Okay. So we can change the environment of a chemical reaction. So we can change the environment of a chemical reaction and apply a stress to the environment. And whenever we do that, we cause a change in the rate of the reaction, the forward or reverse reactions. And the reaction itself is going to try to change this offset of the stress, or however we have affected the environment of the reaction. So if one side of the reaction gains a substance, the reaction shifts to the other side to regain its equilibrium. And if one side loses a substance, the reaction shifts towards that side in order to regain equilibrium. Once again, it's all about regaining that equilibrium. So, for example, if we have, let's say, we are going to add to our reactants. So we add to the reactants are going to increase. Okay, think of it this way. And if we increase the reactants, the reaction, right? The reaction, that's reaction, is then going to try to shift and maintain the equilibrium. So it's going to want to decrease the amount of reactants. So if we are going to want to decrease the amount of reactants, we're going to want to increase the amount of product. So the reaction is going to shift to the right. Okay, so you can sort of set up these little tables to help you understand which way that reaction, that equilibrium reaction, is going to shift to maintain equilibrium. Okay, so that's one example. Also, if we take away R, so if we remove R, then that means the reactants are going to decrease. And the reaction itself is going to want to increase the reactants. So then where's the direction of the reaction going to shift? And it's going to shift to the left, right? To where the reactants are, right? So if this is reactants and this is products, left to right. Okay. So if you remove, shifts left. If you add, shifts right. Okay. And you can look at this little diagram, it'll help you. But just try to understand that concept. So spend a little time thinking about that. And I think we're going to work some problems on it. So heat, oh goodness, what happened with this problem? What happened here? If heat is one of your products, so you have to think of heat in terms of products. So that would be like an exothermic reaction, right? It's one of your products. The rate of the reverse reaction increases if heat is added to offset the stress of adding heat. So this causes the equation, the reaction, to shift to the left. It'll shift to the left. So if you think of temperature, all right, it's one of your products. So temperature increases. That's a product, right? That means your products are increasing. So just think of it in those terms. So if your product, which is temperature, is increasing, then the equation is going to want the products to shift downward, right? So that's what's going to happen next. And so if you want the products to go down to make equilibrium, then you want the equation to shift towards the reactants, which is on the left, right? The reactants are on the left. Oops. Products. So this reaction is going to shift left. Okay. And the opposite is true if this is happening in a cooling environment. Okay. So just, write this down, spend some time with this concept, and make sure that you understand it. Okay. But if you just do it that way, if you follow that format, it'll work for you. So think of temperature as a product. So you don't have to memorize this table. They give you this table, but I think as long as you can understand conceptually what's happening, so you are basically adding this stress, and the reaction is going to want to do the opposite thing to keep equilibrium there, to keep the balance there. And so just think of reactants, products, like left and right. Okay, so if you lean one way, reaction is going to lean the other way. Okay, so try to understand that concept. So let's go ahead and work a few of those problems. Where's my OneNote? Okay. Chapter 9, section 4. Or wait, no, I think this is the right section. I think they're mislabeled. Yeah, this should say, oh no, it's right. We're on section 9.3 actually, right? I said the wrong section earlier. This is right, 9.3. All right, let's work 9.19. What is meant by a reversible reaction? Well, that just means that a reaction, and that's just shorthand for reaction, can proceed, let's say proceed forward and reverse. And that's going to be represented by these arrows. All right. Okay. It's just a reversible reaction. So you can, so the reactants can be reformed, right? So for these kind of problems, you have to know your definitions. Okay. You have to know what it means. So 9.21, write an equilibrium constant expression for the following reactions. A. Okay, so let's write this out. So what is equilibrium constant, right? That's K. So remember that's concentration products over concentration of reactants. So how will we do this for A, where we have carbon monoxide on one side and water in this reversible reaction with our hydrogen and carbon dioxide? So based on what we were looking at earlier, this is A and B and C and D, we would write this then as K equals, so A, K equals, so if you're writing it on your test, I would write out my equation like this. And then you can write your concentration of C, right, times D over, and these are all gases, so we're going to write out all of this. CO, right, and H2O. Okay, there you go. So we've done A, now let's do B. All right, so once again, go ahead and write out your K equals, and it helps you do this on your test too, I think. So what will we have? Look at our equation. We've got acetic acid and water makes the hydronium ion and the acetate ion. So in this reversible reaction, so, and look at what's happening there, right? You can always practice and look, oh, where's my proton donor, so on and so forth, or what's my acid and what's my base. So what do you have? You're going to write your hydronium ion, and that's times concentration of your acetate ion over your acetic acid. And look, we said we weren't going to write liquids, right? So all we do is we write our acetic acid, and we're done. That's it. You don't have to write those states of matter in the equation. It's good just like that. Okay. So let's do 9.23. All right. So for the following values of K, indicate whether the products or reactants are present in larger amounts. So we have our K, and we have our products over our reactants. So if our K is going to be greater than 1, then we must have more products. And if our K is less than 1, we must have more reactants. Okay. So that's because we have more in the denominator, right? More at the bottom. So A, 1 times 10 to the -5th. All right. So are you going to have more in the products or in the reactants? Well, that's way less than 1, right? Move the decimal way that way. All right. So that's definitely going to be less than 1. So there's going to be more concentration in the reactants. You're going to have more reactants. More reactants there. Okay, B. 156. Well, that's a lot more than 1. So that's definitely going to be more in the products. And 1. Well, it can only be 1 if there's the same number on each side, right? 1 divided by 1, 2 divided by 2. So that's going to be equal. You're going to have equal amounts. Because to equal 1, it has to be that number divided by itself. So that'll be equal. Okay. Let's do 9.25. All right. Oxygen and hydrogen gas can be generated if electrical energy is added through the electrolysis of water. And we have this equation. In which direction will the equilibrium shift, right or to the left, if the following changes occur to the reaction at equilibrium? Okay, so we can write out our little table. So if we have what we do, what the reaction is going to want to do, and then the shift, all right, I think this will help us out. So we want to add O2. We want to add O2. So if we are adding O2 reactants, if we are adding, products, if we are adding to the products, the reaction is going to want to do the opposite then and decrease the products. So we are going to shift the equation towards the reactants, and that's to the left, right? Left, right? That's to the left. Okay, so let's write it here. If we want to, so that's A. So let's do B. If we are adding electrical energy, we are adding reactants. So the reaction to maintain equilibrium is going to try to do the opposite thing. It's going to lean the other way then, right? So you can think of it like a seesaw kind of. So I'm doing this, right? So then to balance the seesaw, the other person on the other side of the seesaw, I guess like that's the reaction, is going to try to do the opposite. That is if you want to be level. So then the reactants, so the reaction is going to want the reactants to go down, basically. So the products would be going up. So then you're going to shift to the right. Okay, you're going to shift to the right. So now remove our hydrogen, remove the hydrogen. So that's one of our products. So we are decreasing the products. So the reaction is going to want to increase the products. So then the reaction is going to lean to the right, right? So just make sure we write this in here. Okay. D. Whoops. D. Add water. Add our water. So we want to add a reactant. So the reaction is going to lean away in the opposite direction and decrease the reactants. So towards the products then. And so if you're going towards the products, that would be to the right. All right. So, yep, that's it. That's all you have to do for that one. Okay. So it's just getting familiar with that concept and being able to apply it. That's all it is. So just think of how you want to organize your thoughts. All right. So are we going to do 9.27? Let's do 9.29, I believe, because that one is just the same. So let's do 9.29. So we are opening a bottle of soda, and it eventually goes flat. Oh, that's sad. How can Le Chatelier's, so that's whenever we were talking about the shifting of the equilibrium. So it was on that slide, but I might not have said it out loud, that fancy name. So that's Le Chatelier's principle, right? And that is basically an explanation of how the reaction is trying to maintain equilibrium whenever a stress is applied. So how can that principle explain this using the following reaction? All right, so what's happening here? Well, when I open that top, when I crack it open, when I open the can, or the bottle, it's a bottle, I guess. Okay, when I open the bottle, you are releasing CO2. Carbon dioxide is released, right? There it is. All those bubbles, right? The spiciness, as my niece and nephew call it. So the CO2 is released. And then, sorry, I got distracted by Phil over there. So the reaction shifts. It's going to shift to make more product until it's going to make more product, right? Until my reactant is depleted. All right. All right. So until we are depleted. All right. So let's work on 9.4 now. Now we're in 9.4. So weak acids and bases. Okay. So the same equilibrium principles apply to weak acids and bases. But they only partially dissociate, remember, so that's different than strong acids and bases. And so we have equilibrium in aqueous solution. So your book interchangeably changes the way they decide to write out, whether it's going to be with the molecular formula or drawing out structures in this example, but I'll try not to be too confusing with this kind of thing for you on the test. Just know that these two things are the same thing, right? So you have your acetic acid and you have your acetate ions. All right, it's the same thing. This should be. All right, so for this particular reaction, you can see the equation here, right? And so you have this representation. Oops. Nope. Hang on a second. You have to look at your PowerPoint, right? So make sure you get a look at your PowerPoint. This is a gigantic mess now. A gigantic mess, but look at your PowerPoint. So you are looking at an equilibrium equation, just sort of like we did before. I don't know why I started to write plus. And it's the same thing. You're going to have your reactants and your products, and you are not going to write out liquids. All right, so similar principle. But look at your PowerPoint slide. The formatting is so off on the iPad for some reason. If you need a computer, that might help you out also. If you're going off of an iPad, I don't know if it does this to you too. So the weak acids, so this is a table of weak acids. And you're going to have a table like this on your test. Look at all of the little things that were left off of here. All right, so use your PowerPoints. Okay, or use a PDF version even. So you have your table of weak acids, but some acids that are weak are weaker than others, and some weak acids are stronger than other weak acids. So all weak acids are going to dissociate by giving away that proton, right? So they're not going to completely dissociate, but whenever they do, they're going to do so the same way by donating a proton. And then a hydronium ion is going to be formed in aqueous solution. So every weak acid then has a dissociation constant. It makes sense, right? So that is going to be referred to as the Ka. That is the acid dissociation constant. So A for acid. And so whenever you are looking at this, just understand that basically, so what you have to get this is you're going to have the K with whatever dissociates over what's undissociated. All right, so that's the Ka. So the weaker it is, the weaker an acid is, that's going to be a smaller constant, a smaller Ka. Okay, so the stronger it is, you're going to have a greater Ka. So look how small these numbers are way down here. So water, that's a really weak acid whenever water is behaving as the acid. But for example, hydrogen sulfate, so even though that's going to be a weak acid, still it's stronger relative to these other acids with smaller constants. Okay, so just to give you an idea. All right, so you'll have this table, but you'll have to know this part. Okay, so for weak acids, that constant, all right, so the value of Ka is less than that of 1. And it indicates that you're going to have more acetic acid, right? So more of your acetic acid molecules, like if you look back at that equation at equilibrium, than your acetate ions. So that's exactly what we talked about in class already. So if you're going to have your products over reactants, remember again, so on the reactant side, that was your acetate. Wait, hang on a second. Losing my train of thought. I'm talking too fast. That was your acetic acid and your reactions and your reactants with water, your acetic acid, right? And then you had some acetate ions, right? You had some acetate ions, but a much lesser value, more like 5%. Okay, so that would basically mean that you're going to have a Ka of less than 1. Okay, so because all of those weak acids are going to attain some equilibrium in solution, or they can, so this is going to be for the Ka at a given temperature. So we could talk about different temperatures, but for now, we're just going to do this consider everything at one given temperature. Okay, so there's going to be a different amount to which each weak acid is going to dissociate. So that happens to different extents for different weak acids. And those constant values, therefore, are different from acid to acid. So remember when you were looking at those tables, that's why those constants are different. And that has to do with the ionization strength or size. So the larger the constant, that Ka, the stronger the acid, and the more protons are going to dissociate, right? So that's why, so if you have a strong actual acid, it's going to completely dissociate. So the stronger the acid, it also follows that trend, the more it's going to dissociate. And you're going to have more protons in that solution that have dissociated, okay? And the same thing for a weak base. And we tend to emphasize one more than the other. So if you look at some of those charged functional groups, like you have your carboxylic acid, right, where you're going to donate a proton there, you can see that you actually have the formation of this negatively charged carboxylate, where you had a carboxylic acid here, and you've donated a proton. And so you can kind of follow things on different sides of the equation. So this water picks up a proton and is now hydronium ion, right? Where before you just had water. And you can have functional group like you have this protonated amine, okay, where you can see that hydrogen can be donated, right, in that respect too. And so then you'll, instead of being a protonated amine, you'll become an amine, and the water once again picks up a proton and you have a hydronium ion. So this happens also with your functional groups. And so get familiar with this. So we're going to build on what we talked about already, and we named acids and bases whenever we wrote those chemical equations. And now we have our conjugate acids and bases. Okay, so let's talk about what that is. So whenever we have this reaction, right, we have our acid here, right? So we have our acid on this side of the equation. And if I look over and I say, oh, look, I've got something very similar looking over here, like I have acetic acid and I have some acetate ions over here on this side. And I look, what has happened? Well, it looks like a proton, or this hydrogen, has been given, all right? It has been given. So this is my acid because it's a donor. It's a proton donor. And so whenever you have this reversible equation, so on the other side of the equation, where you have this compound that has this compound where you have, so you can see that clearly, if you follow this compound, you can see that a hydrogen has been lost. So this becomes, so this is an acid, it becomes the conjugate base. And where you have the base, so water acts as the base here, because this water accepts. So if you follow, the water has accepted, right, a proton and become a hydronium ion. So this is the base. Then what it has become in the products is going to be called the conjugate acid. So you're going to have pairs. You're going to have an acid and conjugate base pair and a base and conjugate acid pair. So before we were naming acid and base, and now you have to name the conjugate acid and the conjugate base. So the acid becomes the conjugate base. And so because, once again, you have this compound, if you can reform from your acetate ions your acetic acid, this conjugate base is what can go around and pick up that hydrogen again. Okay, so you're going to call that the conjugate base. So now we have these pairs to think about. We're looking at equilibrium equations with weak acids and bases. Okay, so if you see, all right, you have that acid, it donates a proton to a molecule of water, right? Accepts the proton, and then you have a hydronium ion. Should be positive. So the anion that remains after, right, is the conjugate base of your acetic acid. So that's your acetate ions right here. Because that acetate ion acts as the base in the reverse reaction. So it's just a written form of what I was saying when we looked at the last slide. So the acid, right, the acetic acid, donates a proton to the water, which accepts it, forming the hydronium ion. The anion that remains after the donation, right? Wait, this exact same thing was repeated twice in a row in the same slide. Okay, well, repetition is great, right? I think it was actually supposed to probably talk about the conjugate acid. That's so silly. Anyway, you get the picture, and I explained on the previous slide. I know, how long was it going to take before I realized I was repeating myself? That's silly. All right. So the molecules or the ions related by the loss or gain of one hydrogen or a proton or the conjugate acid and base pairs. Okay, so the weak acids are generically going to be designated as, so A for acid and H for that proton that it can donate, that hydrogen. And the conjugate base then is just your A, and you've lost a hydrogen. So it's like that. So whenever you see that, we're talking about the weak acid and the conjugate base. So that's how we denote that sometimes in science. So if you have a weak base, like whenever you have an amine, it will accept the proton from water to form a protonated amine with a positive charge. So in the case of water, it'll act as an acid. So the protonated amine and amine are conjugate acid base pairs, all right, of that same functional group. So that's just applying what we talked about in terms of functional groups, all right. So you see what happens there, where you have a base that picks up, it accepts a hydrogen, right? So you know that that's your base, and so the one that has picked up the hydrogen is now your conjugate acid. Okay. So there are some rules that you can go through for understanding how to write the products of a weak acid-base equation. You can follow these steps. So the conjugates are going to be on the product side of the equilibrium equation. All right. So it's just like we've always been doing. And you're just going to have acid and base on the reactant side. So you're going to have acid and base on the reactant side. And in the product side, you're going to have your conjugate acid and your conjugate base. Oops. Okay, there you go. So that's basically what that means. So now, look, it's written out in two different ways. Good. So when the proton's donated from the acid, so the hydrogen's donated, it's left, it's pushed out from the acid, the conjugate base that's going to be formed, that's going to pick up that hydrogen, is going to have the conjugate base that's formed with one more negative, than the acid, is going to be one more negative charge than the acid from which it was formed. So whenever a proton is accepted by the base, right, the conjugate acid, so that's when a proton is picked up, the conjugate acid formed is going to have one more positive charge than the base. Don't worry, we're going to work some problems from when it was formed. So you're going to have a difference here of one charge. All right, each time something like this happens, it's going to be a difference of one charge. So the total charge of the reactants is going to equal the charge of the products, right? We're not having anything created or destroyed, so that has all stayed the same. And also, you can apply these weak acids, oxygen transport and Le Chatelier's principle, to something that's relevant to you, which would be the transport of oxygen in your patients. So you're going to have the protein hemoglobin. We've talked about it many times before. It carries oxygen from the lungs to the tissues through the bloodstream. All right, so that hemoglobin, that's in your red blood cells. So it binds oxygen. And hemoglobin also binds protons. But the thing is, it does so with opposite affinity. So it can only bind one at a time. And so through this affinity setup, you have a mechanism for maintaining equilibrium and the presence of oxygen in your blood. So that's pretty cool, right? So you have a tightly controlled binding and release of oxygen throughout your body. It's all a weak acid base equilibrium thing, okay? So we're gonna wait on 9.5. We'll do that in just a minute, and we'll go ahead and work some problems. All right, so 9.4, you're gonna have these tables, but you're not gonna have this giant red arrow. All right, so let's work 9.31. Let's see. All right, I'll leave that table up. So 9.31. So we're going to identify the stronger acid in each pair. Okay, so let's see what we've got here. All right, can we find these things on our tables? So let's see. Let's look to see what we've got on our tables. And can you find it? Yes, you have dihydrogen phosphate ion right here. And you can look at the equilibrium constant. And let's see, what else do we have? We have our hydrogen phosphate ion, and we can look at the equilibrium constant, because we know that as the equilibrium constant is larger, that's going to be a stronger acid, even though it's a weak acid. It's a stronger weak acid. I know, it's kind of confusing. So, A, which one is going to be stronger? Well, it's definitely going to be dihydrogen phosphate ion, this one. Okay, B. All right, so we have our hydrofluoric acid, and so where are we at? Hydrofluoric acid, and we have our formic acid. We've got formic acid. So which one? We look over at their equilibrium constants. And which one is bigger? Hydrofluoric acid for sure. C, hydrobromic acid. Where's this at? Use a different color now. Hydrobromic acid. It is, it's not on here, is it? But you know that this is a strong acid. This is a strong acid. Why? Because I bring clay. You remember that, right? That's a strong acid. And this is a list of weak acids. So do we see our other compound on the list of weak acids? We do. It's nitrous acid. So we have nitrous acid. That's going to be a weak acid. So which one is stronger? Hydrobromic acid, of course. Okay. So 9.33. We need to identify the acid and base on the reactant side of the following equations and identify the conjugate acid and base on the product side. All right, so they give you a lot of information in that question to help you out too. All right, so how shall we do this? All right, we have our hydrogen sulfate. So let's see, what are we going to do? What are we going to do? So we have our hydrogen sulfate and water. So what is going to be our acid and base? So I like to do water first. So let's look at water. So we have water, and look, we have a hydronium ion on this side. So if we have a hydronium ion, then it seems to be that the water is picking up, is accepting a proton, right? It is accepting a proton, so this water must be the base, right? And I'll just abbreviate it this way. And what we have made is going to be the conjugate acid, all right? So the water has picked up that proton and it is now a hydronium ion, and that's the conjugate acid. So I like to get water out of the way first if there's a water there. That's just me. So now what do we have here? This must be our acid, right? And it certainly is our acid. So has donated the hydrogen. So you see here, we are depleted of our hydrogen, and this is our conjugate base, which can then pick up a hydrogen again because that's our reversible reaction. We can reform the reactants from the products. Okay, that's all you have to do, right? So B. All right, so we have this protonated, yeah, so, and we have water, so we can do water first. So, all right, water, once again, has as a base, water has picked up a proton. So this is going to be our conjugate acid. And we have our acid, which, so this is going to be as our acid, can then donate a proton, and you have ammonia, your conjugate base. All right. Pretty straightforward. All right. Oh, nope. Now I don't have water. So how am I going to do this one? Well, I can look and I can follow the cyanides here, see? So I can look on the reactants and the products and see how this has changed, how this compound has changed. It has lost the hydrogen. So this hydrogen is donated. This must be our acid, and this must be our conjugate base. All right. And here we have accepted a proton. So the base is what's going to be on the product side. All right. And that base has accepted a proton on the reactant side of the equation. So that's going to be your conjugate acid. All right. Cool deal. Let's do 9.35. Write the formula and name of the conjugate base formed from each of the following. Okay, so we have hydrogen and fluorine. So let's see what we have here. So how are we going to write this out? So they want the formula and name of the conjugate base for each of the following. So the conjugate base. So this is the conjugate base. So what's going to happen is we're going to lose this hydrogen. So what shall we have then? Fluoride. Okay. And in this case, what are we going to have? We're only going to have one hydrogen, and that's going to become hydroxide. Okay. And what's going to happen in this case? All right. So we're just going to have one HCO3, and we're going to have a negative charge because we lost one of our hydrogens there. And this is going to be, you can look at your polyatomic list. This is bicarbonate. Okay, and what are we going to have here? So we've lost a proton, so we have SO4, and that overall charge on that polyatomic ion is going to change, and now you're going to have sulfate. Sulfate. All right, so on these problems too, remember your adic-itis, adic-itis. All right. So let's do 9.37. So we are going to write the formula and name of the conjugate acid formed from each of these bases. So these are bases. So to form the acid, we're going to pick up a proton, right? So how are we going to write out A? So you're going to go up on the charge overall in this polyatomic ion. So it's just going to be one negative charge and 3. So what you had was carbonate. right? And now you're going to have carbonic acid. Okay, and so here you have water. You just have water. So what are you going to have? You are going to add a hydrogen. So then you're going to have H3O plus, and that is called the hydronium ion. Let's put a little star by that. You got to know that. All right. What do we have now? We're going to add a hydrogen. So we're going to have H3. Oh, my bad. Nope, not H3. That's silly. You're going to have H2. Well, yeah, no, that's right. Of course, I was right. Silly me. You're going to lose your negative charge. So you have H3PO4. So this is going to be your phosphoric acid. Okay, and you're going to have this. And how many times have we looked at this guy? So this is going to be HBr, and that's your hydrobromic acid. Okay, so that's it. That's how you do that. That's how you do that. So let's do 9.39. Complete the following reactions and identify the conjugate acid-base pairs if the named reactant acts as an acid. Okay, so formic acid found in ants and bee stings. All right, formic acid. So, excuse me. So what shall we do? So here, this is our formic acid. And so we are assuming if the named reactant acts as an acid. All right. So what will we have then? So I guess we can write it out right here. So what we will have is we're going to have then our formic acid is going to lose this hydrogen. So you're going to just have this ion now, right? And that's aqueous. And your water has picked up then that, because your water is going to be your base, and it picks up that hydrogen, right? So now you're going to have your hydronium ion, and that is also aqueous. And that's it, except we need to identify everything. So this is your acid, this is your base, and on the other side, this is going to be your conjugate base, right? So this is what has happened to the acid, and this is your conjugate acid. So that's after the base has been affected by picking up that proton. Okay, so dihydrogen phosphate, right, in water. So what are we going to get? So for one, we're assuming that this is the acid, this is the base. So we are going to then have our hydronium ion for one. So that's going to be your conjugate acid. And then what are we going to have for our conjugate base? Well, you're going to, what? You're going to have H minus 2. You're going to increase that negative charge. All right. So there you go. All righty. All righty. So, and you have donated one of your hydrogens, right? And we've labeled everything. So let's move on to C. I think this is the last problem for this section, right? So what are we going to have? All right, bicarbonate, right? So that's in your blood buffering, because you have to maintain that pH in the blood. So your acid is going to be here. So then the water is the base. So once again, you're going to have a hydronium ion, which is going to be, guess what? Your conjugate acid. And I'm forgetting to write aqueous here and aqueous here. All right. So everything. So, and you're going to have, so you're losing your hydrogen here. You're just going to have CO, and so you're going to increase the negative charges. 3, that's aqueous, and that's it. And that's your conjugate base. Okay, that's all you do for those. So now let's go over our PowerPoint. All right, so now we're talking about calculating pH and measuring pH on a pH scale. So water, all right, water has a constant too, so an equilibrium constant, and that's going to be known as the KW, W for water, right? So once again, so like you'll see here, water can act as an acid and as a base, right? And so whenever water acts as a base, would then pick up a proton, become a hydronium ion. Whenever it acts as an acid, it produces a hydroxide ion that is the conjugate base. Okay, so in this reaction, which is always happening in water, that's called the autoionization of water. It's an autoionization. So the equilibrium constant, the expression for water is KW, is going to be written out. So I don't know why you never have anything written in these PowerPoints. Just look at your PowerPoints. So you're going to have equations that you're going to be able to use to apply your equilibrium constants. All right, so we're going to apply these equations and do a little bit of math. So you're going to need your calculator in just a little bit. All right, so I think this is supposed to be hydronium ion hydroxide, or perhaps NPH. Don't know why all these symbols are missing. It's very frustrating. So in pure water, both the hydroxide and hydronium ions are being formed. So in these cases, right, so in this case, your hydronium ions are going to be equal to your hydroxide ions. So if we're given a temperature at 25 degrees Celsius, these values are going to they're both going to be 1 times 10 to the negative 7th molar, and the solution then is neutral. So if you add acid to the water, right, and this hydronium ion is equal to protons, basically, there is an increase in your hydronium ions, and there's going to be a decrease in your hydroxide ions. It's going to make that solution overall acidic. And then if a base is added, right, and that increases and your hydronium ion decreases, it's going to make a basic solution, right? Makes sense. So most aqueous solutions are not going to be neutral, and there's going to be some imbalance there of those ions, the hydronium ions and the hydroxide ions. So most of the time you're going to have some imbalance, all right, between the two. So we look at this graph. It's telling us for our molarity for acidic, neutral, and basic solutions, what's happening with those ions. So in a neutral solution, your hydronium ions and your hydroxide ions are going to be equal to each other, you see. But if it's acidic, you're going to have more hydronium ions, right, and less hydroxide, right? So there's this sort of seesaw going on there. And if you have a basic solution, you're going to have more hydroxide ions and less hydronium ions, right? That makes lots of sense. All right. So the amount of hydronium ions in a solution is what defines the acidity of that solution. All right, so that's basically what we were talking about already in class today. So the concentrations of those hydronium ions, it usually ranges from about 1 molar to 1 times 10 to the negative 14 molar. So that's very close to 0. All right, so very close to 0. Because this is a really big range, and those numbers are more ridiculous to work with, we use the log scale, the logarithmic scale. And that's better for, comparing something like concentration of ions. So if you're taking the negative log of a negatively exponential number, you're going to end up with something, you just have to take my word for it on that one, something between 0 and 14. And so those are much more manageable numbers, and that's why we do that. So you remember the pH scale from 0 acidic to 14 basic. All right. And so those numbers are going to determine the pH scale, that scale that we looked at already in class. And so the pH then can be determined from that concentration of hydrogen ions. And so basically, what I think you're supposed to have on the slide here is that you are having, right, let's see, pH equals the negative log of your hydronium ion concentration. So that's how you're going to find pH. You're going to use this equation. You can measure pH with a pH scale, but you also have this math that you can do this way if you happen to have that concentration. So P is actually meant to take the mathematical function negative of log, right? So that's what the P actually stands for, and the H for pH is actually referring to hydrogen, right? So that's where the term pH comes from. So the negative log, so the P of H, pH. All right. And so that'll help you maybe to remember what equation you have to use. So if you look here, you'll see that reference of pH to whether something is basic, neutral, or acidic. So if you have a solution that is basic, the pH is going to be greater than 7, right? And so here we have a number which is in reference to 7, right? So less than 1 times 10 to the negative 7th. Here you have equals 7, and you have a neutral pH. That's 1 times 10 to the negative 7. And then contrary-wise, if it's acidic, you have a pH that's less than 7. All right, so your hydronium ions are greater, right, than 1 times 10 to the negative 2nd. So acidic is referring to your hydronium ions, basically. Okay. So a lot of times I said you could measure pH with a scale, a pH meter. We have those in the lab. If anybody wants to come up and take a look at what they look like. And we also have just pH strips that people can use. And so that is basically, it's just a type of paper that's embedded with some indicators that will change color depending on the pH of the solution that you use. So you may use these to test the pH of your pool. You've probably seen that before with a swimming pool. So living things, as I said before, they really need to maintain a constant pH. So around 7.45 or so. And this can be measured. It can be calculated depending on if you know the concentration of the ions there. But if you go too far outside of that range of what your blood pH is supposed to be, that's actually going to be very dangerous, right? And so if you look here It's another scale, a pH scale that is just showing you what is neutral, what numbers are neutral relative to the concentration of hydronium ions, and some examples of what fits the category of items, everyday items that are those pHs. So if you are going to calculate pH, all right, so let's talk about calculating pH for a second. If we're going to, I have to keep going in and adding in things that your slides are missing. If we are going to calculate pH, all right, and we are given, for example, that a hydrochloric acid solution is 0.05 molar, it's really easy to calculate the pH. So in that case, so we know that that's a strong acid, and it's going to completely dissociate or ionize. HCl is going to basically equal the concentration of your concentration of HCl is going to equal your concentration of your hydronium ions. So if you're going to have 0.050 molar HCl, you're also going to have 0.05 molar of your hydronium ions, right? Because it's going to completely dissociate. So that's going to be the same number of ions as far as molarity goes. So that's really easy, right? I like that kind of problem. So then pH can be directly calculated for a strong acid. So if you are going to find the pH, you're going to take the negative log of the concentration of hydronium ions. So in this case, it'd be the negative log of 0.05. And so you have a pH of negative 1.3. Just kidding. You cannot have a negative pH. So this is going to actually be just 1.3. Goofy. All right. So, all right. So let's look at 9.5. So you're going to calculate your concentration of hydronium ions, really, most of the time, instead of finding pH from concentration, because most of the time you can just measure pH with a pH strip or a pH scale. If you really want to be more specific, you use the pH scale. So basically, so I had to go and fill in these values again. All right, so if you're going to try to figure out the hydronium ions, you want to know that concentration. So what you're going to do, what you're basically going to do is you'll have your pH, all right, equals your negative log, the concentration of your hydronium ions. So you'll have pH, all right, equals the negative log of your hydronium ions, right? And so what you're going to do is move this negative. So then you're going to have negative pH equals just the log of the concentration of your hydronium ions, right? And so what you have to do with log is you're going to have to do the inverse now of that. And so what it's going to be is 10 to the negative pH, basically. 10 to the negative pH equals your concentration of hydronium ions. Okay, so that's basically how you're going to enter this in on your calculator. So we talked about how to find pH, and now we know and how to do that with the concentration of hydronium ions. And now you know how to find the concentration of hydronium ions from pH. So let's try to do this in a calculator, just as an example. So let's say that I have as my concentration of my hydronium ions, that would be 1 times 10 to the -8. All right. And let's say I want to know what the pH is. All right, so I'm going to have to enter this into my calculator. All right, so I will go ahead and show you exactly how I'll do that. Okay, let me see if I can pull up my camera on here. Yes, so now I should be able to show you. All right, so what I'm gonna have to do is, this is sort of goofy. Okay, so I'm going to hit, all right, there we go. Let's see. So how am I going to do this? So I need to hit, I need negative log, right, for my equation. So negative, and you can find the log button here, negative log of, and I'm going to enter my ions that I know the concentration for. So you're going to hit second E, this button. Well, first, actually, I need to type 1, all right, and it's going to be times, you're going to hit these buttons, 2, so -8, right? So that's how you're going to hit that in. You're going to close parentheses, you're going to hit equals, and it's 8. That's a basic pH with that concentration of hydronium ions. Okay, so that's how you're going to work that kind of problem. All right, so, and let's see, we had, right, we also have our other equation. If we have our pH, how are we going to find our hydronium ions? And I'll show you that too. So I found an example. So let's say, and we're looking at this equation right here, our pH is, let's say 10.8. 10.8. So we're going to have to put in our calculator is 10 to the power of -10.8, and that's going to give us our answer. So how do we put that in the calculator? All right, well, let me get over to my camera. Okay. This is not very elegant, but all right, so you're going to have you're going to hit the second button. All right, so 10 to the power of, if you hit -10.8 and you hit your close parentheses equals 1.58 times 10 to the -11. All right, there you go. That's how you do that. That's what you should get. Okay, so, and now we can switch back over to our PowerPoint. So now you've got some examples of how to use what parameters you have and what parameters you need to solve these problems, to find pH and to find concentration of hydronium ions inversely. Okay. So that's 9.6. So let's go ahead and work a couple of problems. All right. So let's see. 9.5. Okay, so you're going to be given this, but you're not going to be given this. This you have to know. All right. Let's work 9.41. All right. So state if each of the following solutions is acidic, basic, or neutral. So blood, the pH is 7.38. So, and I told you in class earlier, that's slightly alkaline, which is another way of saying that's basic. Okay? Because it's greater than 7. All right, vinegar, a pH of 2.8. Well, vinegar, that's an acid, right? So pH of 2.8, that's much lower than 7. So that's an acid. Drain cleaner, like Drano, 11.2, that's much greater than 7. That's going to be basic. Coffee, right? You ever get acid reflux after drinking too much coffee? I certainly do. So that is acidic, right? Because the pH 5.5 is much lower than 7, right? That's acidic. Okay, so let's do 9.43. State if each of the following solutions is acidic, basic, or neutral. So let's see what we have here. Okay, so basically all you have to do in this one is look at that exponent. So look at the exponent. All right, so we've got to the -8. That is going to be basic. That is going to be basic. And you have everything that you need to enter this in your calculator also, right? So if you have to the -3, all right, then that's acidic, right? Think of your scale and your concentrations. C, if you have 10 to the -11 is your concentration, that is going to be basic. And if you have to the -7, this number, that's neutral. That's going to be neutral, right? So now in 9.45, it wants us to calculate the pH of each of these solutions. And so you can do that first and then say if it's acid or base too. So, all right, so for A, so we have, let's did it again, it's the same, right? So 1.2 times 10 to the -8. So if you put that in your calculator, all right, so you're going to have, so then pH, right, is equal to, so then you're going to have pH, it's equal to the negative log of 1.2 times 10 to the -8. So you're going to type that in your calculator, and the pH that you're going to get from knowing your ions, because we're not using a pH scale here, this is what we're given. Your pH is 7.92, and that is basic. Okay, so B, if you work that out, you're going to get 2.15. All right, and you're working it out just like this. It's going to be the negative log of 7.0 times 10 to the -3. And so this is indeed acidic. Okay, let's see if we have the negative log of 4.7 times 10 to the -11. You're going to get about, or exactly, not about, 10.33, and that is basic. Okay, so that's what we got before, right? Basic, yeah. So D, 7, this is going to be neutral. So put in your calculator the negative log of 1 times 10 to the -7, and you are going to get 7, right? So that's neutral. All right, that's neutral, exactly neutral. Doesn't happen a lot. So, but here's a problem like that. Okay, so do we have any more that we're going to work? Yes, there's one more. Okay, so we are going to calculate the concentration of hydronium ions for each of the following measurements of pH. So hand soap, okay, so how do you do this? This is going to be 10 to the negative pH. That's how we're going to figure out the concentration of hydronium ions. So then 10 to the -9.5 is going to equal 3 times 10 to the -10 molar, right? So B, for seawater, you're going to do the same thing, and it's going to be 10 to the -8.2 then, right? So you'll get 6 times 10 to the negative 9. Okay, and if you have 10 to the negative 3.5, you're going to get 3 times 10 to the negative 4, right? This was 9. And here, 10 to the negative 4.5, you're going to get 3 times 10 to the negative 5. And what unit are these? Molar. Don't forget your units. Okay, that's it. Thank you.